Hello, hello. How's it going? So I ended up being able to put a bearing load on the bottom one because it was not letting me because there was two lines in the mesh, I guess. And it wasn't treating it as a cylinder, it was treating it. So that worked. And then I was able to calculate the approximate like force to equal out the moment. And it didn't work with the frictionless support. And I also tried the cylindrical support, which seemed good. Then you would just leave the tangential free and then radial and the other two would be fixed. But it's still not working. I have it pulled up. I don't know if I'm looking at it right now or
let's take one after. Yeah, I need to fix this thing. Yeah.
Seems to do a lot of great things. So and like he knows like 5 steps ahead. The Minnesota equation too.
Yeah, that was. Yes.
Right, it's 4 o'clock. Let's go and get started. It's looking like the camera and the mic experiencing some technical difficulties. So if the sound ever cuts out during the Zoom, just someone type in the chat that you can't hear me. So I'm hoping, I'm thinking I made it stable, but we'll see. That's why I kind of have the camera. Usually I don't like to have the camera on the side because it's weird to look at myself, but I have to see if the camera's going to crap out again. All right, so good afternoon, everyone. How's everyone doing today? Good. All right, so we're end of week 11. Everyone looks pretty tired. I'm pretty tired too. It's been busy, but we're going to keep trudging right along. And so today we're finally going to finish up our lecture notes on human motion kinematics. And so we just have a little bit more to go on that. And then we're going to start the next lecture notes on dynamics. Okay. All right. So I think it's most of my announcements. So over the last couple of weeks or so, I know a lot of groups have reached out to me in terms of what they want to do for the final project, which is great. I took a look on the Discord channel today. I saw there was some chatter about it too. And so I haven't officially written down everything yet, although I've gotten everyone's emails about it. But I think probably what I'm gonna do tomorrow is I'm gonna write down all the groups that have reached out to me so far, how many members they have in their groups, and then try to start filling some spots because after this week we have maybe about a month and a half until the end of the semester, and so I think everyone should either decide a topic or be in a group by next week. Okay, and so I'll put that together by tomorrow, and then if you're not in a group, I'll probably be reaching out to you, and if you still have some space in your group too, then I'll probably reach out to you too, and we'll try to play matchmaker over the next week or so.
Do you want me to email you with my group?
Yeah. So even if you talk to me, I know quite a few people come talk to me in person, just so it's easier for me to kind of search up and put together a document. If you can email me, that would be great.
Okay.
Mm-hmm. All right, and so I think that's all my announcements. And so, are there any questions I can answer before we get started?
We can still email you about our group.
Wait, say again?
Like we still email you about like.
Oh yeah. I'm mostly concerned, just to make sure everyone is in a group, because yeah, we're going to be a little bit tight just because we do have 42 people in the class, and so I want to make sure that we have enough time for everyone's presentations, and so I want to limit it to maybe around 8 to 9 groups overall, that's kind of my main concern, and so. But of course, the sooner you pick a topic, the better, just so you can start working on it. Because the deadline is going to be on you kind of sooner than you think. All right. Any other questions on any of that?
I mentioned this already, but does the midterm include this homework set?
Yes, it does. Yeah. So the upcoming midterm. So the next midterm exam is going to be on November 17th. So we'll probably talk about it next week. And so I'll put the study guide out there next week, and I'll probably record a review video, but it's only going to cover homeworks 4 and 5. Yeah. Okay. All right. So let's go ahead and pick up where we left off. And so this set of lecture notes has actually taken me a lot longer than I thought it was going to take, but that's fine. There's a lot going on here, so I'd rather take my time with this and make sure it's explained thoroughly rather than try to rush through it. And so for the 4th time, we are going over human motion kinematics. And if you remember, this whole topic here, or this whole chapter is all about how can we quantify and how can we describe human motion in a systematic, quantifiable way. All right, and so like I mentioned before, we're taking a fairly modern approach to this, and so we're going over how do you go from motion capture data to actual numbers. Okay. And kind of the crux of our whole analysis, kind of the key to kind of everything, is this concept of transformation matrices. Okay? So I think we spent the better part of 2+ lectures so far talking about transformation matrices, and we're going to finish talking about them today. And so the idea with these transformation matrices is that there are these matrices that describe, in essence, they describe the relative orientation between 2 different reference systems or different coordinate systems. Okay? So understanding transformation matrices, how to compute them, how to interpret them, how to extract useful information from them, that's kind of what this whole unit is all about. And the reason we are spending a lot of time on it is because I think, first of all, it is a little bit difficult to visualize, just because you're taking kind of what I think a lot of people consider as a very visual concept in terms of watching human motion and putting it in terms of numbers, and so that already is not an easy process. But then, once you get the transformation matrix, it's still a little bit hard to kind of work with it. Okay. And so the example that we did last week was all about kind of a realistic situation. And so if you recall, we were looking at the a motion capture system on a leg. So here's the leg. Oh, the kneecap, that's weird. Okay. And so on this leg, what we did was, we took the motion capture markers. And so, let's say the mocap markers are like this, okay? And using those 3 markers, we defined the coordinate system that's attached to the lower leg. And so this XL, YL, ZL right here, this is the coordinate system that's attached to the lower leg. Okay. And remember, we defined that coordinate system based on the motion capture markers that we had, okay? And so to describe kind of the orientation of this coordinate system, we compared it to what we call the lab coordinate system. Okay? Okay. And so this purple XYZ here, this is what we call the lab coordinate system. Or in other words, we call this the stationary coordinate system. And so whenever you're talking about transformation matrices, remember, it's always kind of the relative orientation between 2 different coordinate systems, okay? And a lot of times, that other coordinate system that you're comparing it to is some kind of fixed coordinate system within the room, okay? And so this lab coordinate system, or the stationary one, maybe the origin for that coordinate system is like in the corner of the room or something, okay? It's mostly just used to serve as a reference point to measure all the other stuff, okay? Because even though the leg, the coordinate system that we have in green that's attached to the leg, that's going to start to move around. And so as the person starts to move, they start to jog, they do jumping jacks, whatever, that coordinate system is always going to stay fixed to the leg. And so that's going to go kind of all over the place. So it's going to translate, it's going to rotate, all according to how the person moves. Okay. And so in order to kind of properly track that, we need something that's fixed to kind of always serve as a reference point. Okay. It's the same as, when you're measuring anything. So when you measure, how long, a table is, what you're actually measuring is, the distance of one edge of the table relative to the other. So you always need something to reference from. And that's what this stationary coordinate system is. Okay? And the benefit that we have for this is we know that this is never going to move. And so, we're going to assume we're not doing this analysis on a moving truck or anything like that. So, this is always going to stay fixed. And of course, to quantify the relationship between these two, we spent a good amount of time last week computing the transformation matrix. Okay. And so that R matrix here, this is our transformation matrix that we computed last time. Okay. And if you remember the kind of the convention that we use is that, we kind of read this from right to left. And so what this transformation matrix in this form basically says that if we have coordinates that are in the shank coordinate system, which is the lower leg, okay, and we multiply that by the transformation matrix, it'll give us the corresponding coordinates in the lab system, okay? But believe it or not, that's not as important. So kind of the only thing that I think really important to know about these transformation matrices is that they describe relative orientation, okay? All right, so that's kind of a recap and a little bit of a step back of what we did last time, because I know last time we kind of dove pretty deep into the numbers, and so whenever you do calculations like that, I think it's really easy to kind of lose sight of what's kind of important or why we're doing this. And so today I wanted to start out just to say that this is why we did it, and this is kind of what it represents. Okay, so then now as we kind of finish today's lecture up, you'll have kind of a better understanding of where that comes from. All right, any questions on that? Okay. All right, and so far, the transformation matrices that we have, they only describe rotation. Okay, and so it's actually kind of more fair to call these kind of rotation matrices rather than full transformation matrices. Okay. And so far, we're only considering rotations, and so now we're basically kind of assuming that the two coordinate systems are kind of right on top of each other, and then to get from one to the other, we just kind of perform some rotations. Okay, but of course, that's not always true, because if you just look at this example here, the two coordinate systems that we're considering, the lab frame and the shank frame, they're physically separated by some distance as well, and so there's some translation as well. Okay. And that's going to be important because, when we compute transformation matrices, ultimately what we want are transformation matrices between adjacent body segments on the body. There's going to be some translation there as well, because two body segments, they're not physically located in the same place. Okay. All right. So to kind of highlight this, and so let me go ahead and draw. Okay. So let's say that we start with the coordinate system XYZ like this. Okay. What can happen is that if we kind of move this coordinate system, or we define a new one that's just over here. So we'll call this X prime, Y prime, and Z prime. Okay. What if we assume that between X and X prime, and so between the original coordinate system and this new one right here, there's no rotation that takes place. Okay. Okay. Another way that we can say that is that X and X prime are parallel, Y and Y prime are parallel, and Z prime are all parallel to each other still. Okay. So the coordinate system itself, there's no angle, theta, phi, or psi that describe this. but they're obviously two different coordinate systems, right? One located on the left side of the page, the other one's on the right side of the page. Okay? And so when we move from one point to another, one way that we can describe that is with a vector. And so I'll call it P just for, just to give it a name. And so this P right here is what's called the translation vector. And so that describes kind of the physical distance or the physical translation that a coordinate system has to move, to go from one to another. Okay. And so what we can do is we can add this information into our transformation matrix by simply just augmenting it. Okay. So before, let me use kind of the example we did last time. And so from the example we did last time, we defined this transformation matrix lab R shank, okay? And maybe this is a 3x3 matrix, right? And so we'll call this R11, R12, R13. Okay. So that's kind of the result that we got from at the end of the last class. So this is the this 3x3 matrix. This 3x3 matrix describes the relative rotation between the two coordinate axes. Okay. Let's go ahead and augment this with the P vector. For the P vector, I'll say it's like this. So Px, Py, Pz, okay? So that's the translation that the new coordinate system is going to have relative to the old one, okay? And so if we augment this, all that means is basically we're just going to take this P vector and put it in. And so our lab R shank now is now going to be a 4x4 matrix. And so we're going to have the original R11, R12, R13. Okay. So that was, and so we keep the original rotation, the original transformation matrix, we keep those, the same. We're not changing those values. The only thing that we're doing is we're kind of adding the translation information just kind of right to the side. Okay? And then to kind of make sure it's still a square matrix, we kind of add this kind of last row. It's kind of a dummy row, but it's basically 0, 0, 0, 1. Okay. So this transformation matrix covers both rotation information as well as translation information. So that's all you have to do is just, whatever the translation vector is, you just put it to the right of the matrix. Okay. All right, and so if you've been looking at the homework, for the kinematics problem, I gave you two. So there's a 2D problem and a 3D one. You might, if you're looking at the solutions, you might think, this looks like a mistake. So for the 2D transformation matrices, I'm giving you a 3x3 solution. And so for the 3D problems, I give you a 4x4 solution. It's not a mistake. And so those extra dimensions are given for the whatever the translation vector is going to be. Okay. All right. Any questions on this? Okay. I'm going to do just a very quick example just to show you how to compute this this translation data from from marker data. All right, so let's consider example. Let's say that we have reference frames that are attached to the tibia and the femur. So the tibia, remember, is the main the main bone in your lower leg or the shank, and the femur, of course, is your thigh bone. So that's the upper leg. Okay. All right, and so because we have a coordinate system attached to two different parts of the bodies, each of them are going to have their own origin as well. Okay, and so we can describe the location of the origins using XYZ vectors, but of course the locations of these origins, they have to be relative to something, and so the locations of these origins are given relative to the fixed lab frame. Okay. So for the tibia, okay, so the location of the tibia's basically origin is 45 centimeters, 75 centimeters, and 30 centimeters. Here we have 35, 80, and 55. So based on this information here, let's compute the translation vector that goes from the tibia to the femur. All right, so this is hopefully this is pretty straightforward. We did quite a bit of this last time, although not exactly in this context. But remember, to get a vector that goes from one point to another point, you just have to subtract their x, y, and z coordinates. Okay. Okay. And so our translation vector, P vector here, and we're going from the tibia to the femur. And so we're going to start with the femur. We're going to start with the femur's coordinates and then subtract the coordinates from the fibula, okay? Or from the femur, tibia. Yes. Is that enough or you want more? Okay. So that's basically how you do it. And so, you just use your kind of your basic vector algebra here, and then, that gives you the translation vector. And so once you compute kind of the rotation vector or rotation matrix between, say, the tibia and the femur, then you can just augment the matrix with this information. Okay. All right, any questions on this? Okay. All right. And so, I have one more section in the kinematics here, and this kind of puts it all together. Okay. So let's talk a bit about how we generally compute joint angles from a motion capture system using unconstrained inverse kinematics. Okay. Okay. All right, so hopefully this section here will kind of do a good job of kind of pulling everything that we've learned over the last couple of weeks into kind of one cohesive lesson. All right. And so let me start by kind of reminding you that, when you have a motion capture system, for each body segment, you actually have two reference frames per body segment. Okay. On the one hand, we have the what we call the tracking coordinate system. Okay. Remember, the tracking coordinate system is comprised of tracking markers that are easy to track, and so they're put in locations that a camera will be able to see it at pretty much at all times. And then we have the anatomical coordinate system. And so the anatomical coordinate system, this is a coordinate system that's more attached to the underlying skeleton or the underlying bones. And this is what's actually used to compute the joint angles. The only caveat is that these ones are harder to track. Okay, so we have kind of both of these at the same time. So if I draw kind of a, let's use the entire leg kind of as a reference system again. Okay, so I'm gonna draw the leg from a side view this time. And so let's say this is a leg right here, okay? And first, let me draw the bones kind of on the inside of the leg, okay? They're not accurate to what they actually look like, but, get the job done. And so the bone in the upper leg, remember, this is called your femur. And without an E, I'm smoking. And the bone in your lower leg, this is your tibia. Okay. Ideally, we would have coordinate systems that are attached directly to these bones, okay? And so the coordinate systems attached to these bones are anatomical coordinate systems, okay? And so that means the relative rotation or the relative angles between these two bones, those are the joint angles that we seek. Okay. So that's our goal. And in a motion capture analysis, we want to find out, what's basically what is the transformation matrix between the femur and the tibia. Okay. Okay. And so if we can compute this, or the inverse is fine too. So if you have tibia R femur, but I just wrote femur R tibia. If we can get that, then we're golden. That's all we need, because from that, we saw at the end of class last time, we can compute, what are all the rotation angles between those two, and then we can take those and put it into a dynamics analysis. Okay. So that's our ultimate goal. The problem is, this is really hard to track in real time, because remember, the anatomical coordinate system, we may or may not see it at all stages of the motion just based on where the markers are. Okay, so we have to kind of compute this in an indirect way using the tracking coordinate systems. Okay. Okay, so let me use green here. All right, and so surrounding these bones are the body segments, and so that includes all the muscle, the skin, the fat, blood vessels, everything around it. Okay. And so the upper leg segment we often call the thigh, and so the thigh kind of encapsulates everything that's around there. Okay. And for the lower leg, we'll call it the shank. I think most people call it your lower leg, but shank is easier to write. Okay. And so we can track the thigh and the shank with coordinate systems, and those would be our tracking coordinate systems. Okay. Remember, we're going to place the tracking markers on the thigh and the shank such that we're always going to see them. And so you can assume that we always have information on that. Okay. In addition to that, we can't forget the lab. So we also have our stationary coordinate system here as well. This is the lab system. All right. So we have five coordinate systems here. So we have the lab stationary coordinate system. We have the femur coordinate system. We have the tibia coordinate system, the thigh coordinate system, and the shank coordinate system. Okay, so 5 coordinate systems. I've tried to color code them to make them kind of easily trackable, so you can kind of categorize each one. And we're going to use those 5 systems to get this right here. Okay. And remember, the reason we need 5 systems in such a complicated setup is because we can't actually track the femur and the tibia at all points in the motion. Okay. So we're going to use the transformation matrices. We're going to use the ones that we can compute and the ones that we can track at all times, and use the properties of the transformation matrices to basically get what we want. Okay. All right, so that was kind of a big, a big setup, but hopefully, with the colors and everything, that makes it clear. Are there any questions on this? Okay, all right. So next, let's talk about the transformation matrices that we can compute easily, and how they're all related to each other. Okay. Okay. So first, let's do the transformation matrices that we based on the tracking coordinate system and the lab. Okay, so so this is basically just like the example that we did last time. And so we have lab R thigh and lab R shank. So these are transformation matrices of the tracking coordinate system and the stationary coordinate system. Okay. And so these are basically available to us at all times because we know where the lab coordinate system is. The lab coordinate system is not going to move. It's just going to sit in the corner over there. And tracking coordinate systems, we've designed these to know these at all times. Okay. So those ones are good. So we don't have to worry about those ones. Okay. So what about the kind of the parallel transformation matrices with the bones? So we have lab R femur and lab R tibia. Because we can't track the anatomical coordinate system at all times, these ones we actually don't know. And so these are basically unknown to us. Okay. We may be able to track them at certain points in time, but not enough to kind of reliably know this enough. Okay. All right, so that's all the transformation matrices relative to the stationary one. Okay, what about between the ACS and the TCS, the anatomical coordinate system and the tracking coordinate system of the same body segment? Okay, so that's going to be, let's do femur. Okay, and tibia are. And so these are okay. And so these are the transformation matrices between the tracking system and the anatomical system of the same segment, right? So the femur and the thigh, that's the same segment. The tibia and the shank, that's the same segment, okay? All right. The interesting thing about these is because, even though, they're different systems, they're still attached to the same segment. And so they're going to move together, right? I know we've talked about before about, when you consider soft tissue like muscle, fat, stuff like all that's going to bolt and stuff like that. But relatively speaking, if you have a coordinate system, if you have a tracker that's directly attached to, your bone and one that's attached to your skin, they're going to move together in relatively the same way, or any kind of like jiggle or anything like that can be okay. So what that means is that, because they move together, the transformations are also going to be constant as well. Okay. And so these are actually going to be constant matrices. And so what's good about a constant matrix is that we just have to compute it once, and then, it doesn't kind of really matter what happens after that because we know its value, okay? And so even though these transformation matrices, they involve the anatomical coordinate system, the femur and the tibia, in this case, we don't actually have to track the femur and the tibia at all times to know what these matrices are. And so if we just compute their value once, then, we'll always know them because they're not going to change, okay? And so what happens at the beginning of a lot of motion captures that there's always a calibration step. And so what's going on in the calibration step is that, if you're in the mocap suit, they might ask you to kind of pose in kind of a weird way. And so the purpose of that is to kind of put your body in a position where both the anatomical and the tracking systems can be seen at the exact same time. Okay. And then what's happening is that the system is then going to compute these transformation matrices and then store them because they're not going to change. Okay. So this is kind of our link. And so this calibration step and these two transformation matrices, these are kind of the link that we need between the anatomical and the tracking coordinate system. Okay. And so what we're going to do now is that remember this is our goal right here. Femur, R, tibia. Okay. And so what I'll show you is that you can actually use these 4 transformation matrices to get the one that we need. All right, any questions on this? Okay. All right, so let's put it all together. Okay. So remember, our goal is this one. Because if we can get the transformation matrix between the femur and the tibia, then we can compute the joint angles directly off that matrix. Okay, so that's our goal. Okay, and so let's use the information that we have here together with some of the properties of transformation matrices to see how we can get there. Okay, and so let's start. We know that we're going to need femur up here in the top left, and so let's start with one of the transformation matrices that has femur in the top left, which is this one. Okay, so we're going to start with femur, or thigh. And basically where we're going to go from here is we're going to cancel out all of the inner dimensions or all of the inner coordinate systems until we get the one that we want. Okay, and so now we need something to cancel out with the thigh. Okay, and so what is a coordinate system here that has thigh? We have this one right here. Okay. Is we have thigh, R, lab, okay? Of course, we don't have this one exactly. We have lab R thigh. And so remember, what we can do is we can use the property of transformation matrices where we can just take its inverse. Okay? So this right here is equal to lab R thigh inverse, okay? And so even though we don't have the exact one that we want, we have the ones we have the right two. We just need to take the inverse to kind of swap their positions. Okay. Okay. Let me zoom out so we can see it all here. All right, so now we've canceled out the thigh, right? And so these two are going to cancel out here. And so that's good. Now we need something to cancel out with lab. Okay, so we need another transformation matrix here that has lab. And we're going to use that one right there. Okay, so we're going to have lab R shank. Okay. So that's going to cancel out the lab right there. Okay. So let's go ahead and cross off the ones here as we use them. And so we've used this one. We started with that one. Then we use this one. Then we use that one. Okay. The last one we're going to use is this one right here. Okay. And we're going to need its inverse. Okay. And so remember, because we have shank that's kind of on the inside right there. And so let's have shank our tibia. Okay. Where of course this right here is going to be tibia or shank inverse. Okay. And so we're kind of really making use of the property where if you multiply transformation matrices by each other, you're going to cancel out that kind of inner dimension. Okay? And so we perform all of this linear algebra, and it is a lot. And so, you know, it's a lot of 4x4 matrices you're multiplying by each other. You know, but this is probably somewhere where you would use like a MATLAB or you use your calculator or something to perform it for you, because otherwise it would take too long. Okay? Look and see what we're left with. And so the thighs cancel out, the labs cancel out, the shanks cancel out, and all we're left with is femur on the left and tibia on the right, which is exactly what we want. Okay. So I'll say after lots of many. Lots of math, so lots of adding, subtracting, multiplying, all that good stuff. Okay. Right. So it was a really roundabout way to get here, but you know, if you look at the four matrices that we use to do this calculation, all four of those we know. You know, they're either constant matrices, which we found out at the beginning, or they're matrices that we kind of always know their values no matter what the motion is, because they're part of a tracking system. Okay, so this is basically the kind of the algorithm or kind of the methodology that you would use to compute this system. Okay? But I think in the homework, I don't have you do this in 3D because it's kind of way too much. But I do have you do this for a 2D system. Okay? So I think that's problem 2A. We're going to do this. Okay, so it's kind of important to know how you kind of go about this. Okay? Trust me, when you're doing it, you're on your own by hand with the 2D system. It goes a lot faster than what we went through here. All right, any questions on this? Okay, all right, so that's it for kinematics. And so with that, you should be able to do problem 2 on homework 5, because problem 2 is kind of all about this stuff. 2B is a 3D problem. And so I think on the homework, I listed it as a challenge one. And so, you know, it would definitely be good to try it. But, you know, it's kind of a little bit too much linear algebra, you know, that I would like normally for something like this. And so, you know, give 2B a try, but you should know how to do 2A from here. So you have about 25 minutes left in class. And so let's go ahead and move on to the next topic, which is inverse dynamics. And so, you know, and so if you kind of remember from your first physics class that you took on general mechanics, you know, the first thing that you learned was kinematics, and then what followed right after that was dynamics. Okay, so we're kind of following the exact same trajectory here. Okay? And so now that we know how to measure and quantify and describe the motion, we're now ready to start talking about, you know, what forces and what moments are causing that motion. Okay? And so whereas the last section was all about angles and velocity and accelerations, we're ready to kind of take that information and turn it into forces and moments. Okay. So this is kind of the connection between, what we've been doing and kind of the first part of the class, which is, all about static analysis. Okay? And so if you remember from static analysis, we were interested in determining, what are the muscle forces and the joint reaction forces, that are needed to produce certain positions. And so we're going to be doing the same thing, but for motion. Although because motion is quite a bit more complicated, we're going to be a bit more limited in what we can determine. Okay. And so, when we do our inverse dynamics analysis, all we're going to be able to compute is just whatever the net forces and the net moments are at each of the joints. Okay. So basically, we're going from a place where, we observe the motion. And so let's say we observe someone do a jumping jack, okay? We can track that motion. And so we can describe, what are the joint angles, joint angular velocities and joint angular accelerations as the person goes through the motion. So we can describe all that. And so the next step is, what are the net forces and net joints, net forces and net moments at the joints that are causing this motion, okay? But we aren't ready yet to talk about individual muscle forces just yet. Okay. Because the difficulty that we have with motion is that because there's so much redundancy in the human body, and so if you're talking about, let's say a simple action, let's say flexing at your elbow, there are, several different muscles that are responsible for that, okay? And so we need to dive into what we call muscle force optimization to compute, what are all the individual muscle forces, but, we'll save that until after this, okay? But just know that, as we go through our inverse dynamics analysis, we're only computing the net effects, okay? And so as an example, let's say that you have a force system on a particle here, okay? And so let's say that we have 5,000 newtons going to the right and 1,500 newtons going to the left, okay? This right here is what I would consider to be like a full force system where you have every single individual force quantified on the particle. And we can see their magnitudes and directions. Okay, and so from inverse dynamics, we're actually not going to be able to get a full system like this. All we're going to be able to see is the net effect. Okay, and so if you kind of add the forces together, you're going to get a net force to the right of 3,500 newtons. Okay. So we're basically going to start with computing this, and then we can move on to muscle force optimization after that. Okay. All right, so that's kind of where we're going. And so, doing the kinematics is one thing, but understanding the muscle forces and torques and moments, that's kind of the next kind of logical step. Any questions on this? Okay. All right, so, but before we get into the math, we do have some new, some new lab equipment to talk about. Okay, and so in the last section, we talked a lot about motion capture setups. So when you're talking about inverse dynamics, you need a way to measure external forces on the body. Okay? And so I'm just going to talk very briefly about a very common piece of lab equipment, which is called a force plate. Okay. All right, and so what you'll see very soon is that whenever we perform an inverse dynamics analysis, there needs to be some kind of external force on the body. Okay, and that's kind of needed to just complete the analysis. And so there are a lot of different ways you can measure external forces on the body. When you're talking about kind of the most common force that's applied on the body is from the ground, and so a force plate is kind of the perfect tool for measuring that. Okay. And so the way a force plate works is that it's basically just like it's very similar to the bathroom scale that you have in your house. Okay, except of course it's a lot more sophisticated. And so what it looks like is that it looks like kind of like a scale. Okay? And so maybe it looks something like this. And so it literally looks like a plate that's on the ground. Okay. And then right underneath this are a bunch of load sensors. Okay. So those load sensors are designed to measure, first of all, compressive forces. And so if you push down on it, it can tell you the weight. Okay. But a lot of these load sensors are also designed to measure, shearing as well. Okay. And so when someone steps down on this, and the ground is going to, produce an equal and opposite reaction. So let's say someone is walking forward, and so they just kind of step down in their stance phase, and they're just kind of pushing off to move forward. Okay, and so that means that there's going to be, of course, a component of the reaction force that points upwards that opposes their gravity, but there's also going to be a component of the ground reaction force that pushes forward because the person is walking forward. Okay, and so a force plate is designed to kind of measure both of those. Okay. And so, and kind of roughly, just we're not going to get too much into the science of it, but the way it works is that when you step on a force plate, what's going to happen is that the force plate is going to compress down a little bit, okay, and it's going to cause the load sensors to deform. And so, what the load sensors are designed to do is that based on how much they deform, based on their deformation, they release a signal or voltage. And you can calibrate that, and you can measure to determine what's the relationship between the voltage and the displacement, and then you can use that information. You can process it in a computer to determine what's the force that's being applied onto this first force plate. All right. Any questions on this? Okay, all right, so let's talk about the inverse dynamics algorithm. And so remember, our goal is to compute, at each of the joints inside the body, what's the net forces and net moments that are needed to produce motion. Okay. Right. And so to do this, we're going to need a lot of information. And so, it's quite a lot of computing to do, but there's a lot of information we need to feed into the system. Okay. And so let's make the following assumptions. All right, so let's assume that we know the following information kind of before we start. Number one is some kind of representative model of the subject. So that one's pretty straightforward. And so a lot of times you're going to have this kind of automatically. But we basically need some kind of physical representation of the human body. Okay. And so for a simplistic case, oftentimes we use kind of like a stick figure model where we represent each body segment as like a rigid rod, and then we do the analysis from there. Okay. So what all this is basically just a representation . Okay. And so we often are going to use this kind of rigid rod model. And so the example that we're going to run with for the legs, it looks something like this. And so let's say that we have a foot, and then connected to the foot is the shank. And then connected to the shank is the thigh. And then connected to the thigh is, let's say your torso. Okay. So of course, this looks absolutely nothing like a human person, unless it's, very, very slender man. But, we just need something that'll work. All right, Number two is the subject's joint kinematics over time. And so remember, this is all the joint angles, the joint velocity, joint acceleration. So this is all basically the output from our kinematics study. Okay. So basically everything that we just did with transformation matrices and all that, we'll assume we've done all of that already. And we are just working with, the joint angles, joint angular velocities, and joint angular accelerations. And number three, we'll also assume that we'll know some kind of measurements of the external forces on the subject. Okay. And so oftentimes this is going to come from a force plate. And so in the example that we'll do, we'll assume that we know, the force plate measurements, but you can also obtain these in other ways as well. But, you have to know you have to have some measure of, what are the external forces acting on the body. Okay. All right. And so, we're going to assume that we know all these three things. And so, we're going to use them going forward. Okay. All right. So knowing all those things, the procedure is something that's not overly foreign to us. And so, we did a lot of this, especially in the early part of the class. Okay. Okay. And so using this information, all we're going to do is that we're going to form three key equations for each body segment. Okay. And those three equations are, equations that we've known and loved. So those are going to be our equations of motion, which is going to be the sum of the forces on the object, both in the X and Y directions. And of course, we're limiting ourselves to 2D here. And so we're going to sum the forces in the X and Y direction, as well as sum the moments around that body segment. Okay. And so we'll have some of the forces in the X direction, some of the forces in the Y direction, and some of the moments. Okay. Of course, this is assuming 2D. And so if we're in 3D, we're actually going to have 6 equations, which makes it even more difficult, or say more tedious. Okay. The difference here is that we're not going to set these equal to 0, because if these were all equal to 0, then we would have a static analysis, and we'd be doing the exact same thing we did before. But instead, we're going to set these equal to kind of their second Newton's law, which is mass times acceleration in the X direction, mass times acceleration in the Y direction. Okay. And so the sum of the forces are going to be equal to that. Where AX, AY, these are the accelerations. Of the body segment center of mass. Okay. So each body segment is going to have its own center of mass, and it's going to be accelerating. Okay. So that acceleration is also going to be changing with time, unless you have a constant acceleration, which is quite rare. Okay. And so these equations here are also going to change with time. Okay. And for the moment equation, we're going to set that equal to I times alpha, okay, plus this extra term here called R cross MA. Okay. All right. So this is probably the term that we've seen the least here. So I, of course, here is the moment of inertia. The body segment. Okay. Alpha here is the angular acceleration. Okay. Okay. And then this extra term right here, this is kind of like the rotational moment from the center of mass. Okay, but you can eliminate this term if you sum the moments around the center of mass. Okay. And so just like the static analysis, it's going to matter, where we sum the moments around. And in this particular case, the most convenient place is to sum them around the mass center. Okay. Because you can deal with that term, of course, but it's kind of annoying to do so. And so, the better thing is just to sum it around the mass center, and we don't have to worry about it. Okay. All right, any questions on this? Okay, all right, so that's all we got time for today. And so we'll pick this up on Tuesday, and we'll pick it right up with an example. And so what you'll see is that, we're gonna apply these three equations here to each segment. And so we're actually gonna use kind of the lower leg model here. And we're gonna see how this is formed. Right? All right, so thank you guys for coming today. Tomorrow, remember tomorrow I'm gonna put together a list of all the groups that have reached out to me so far. And then try to start filling in people just so everyone knows what group that they're in. Okay? And so if you've talked to me, about what group you're going to do or what you're going to do, just please send me an email anyway, just so I can have it just on record. And so I know I've verbally committed to a lot of people, but it's going to help me put the list together if I have emails from everyone. So if you haven't emailed me yet with the group, please go ahead and do so. And then, hopefully by next week, everyone will have a group. All right. So thank you guys for coming today. I hope you guys enjoy your weekend, and I will see you next week.
Semester are you taking the subject 540 computer application engineering design?
I just noticed today that it's being taught. I taught it last time, and so I don't know. And so I would say there's probably a 70% chance that I'll.
Okay, is there any other subjects that you're taking for the master's level?
So I think I probably will be teaching all graduate level courses, and so one that I've taught 3 times now is 417, which is a computational heat transfer. And so I probably might teach that one. I do want to teach so I have another special class that's kind of goes along with this. It's called 442. So that one's all about.
That's the computer aided machine, like the designs, the advanced CAD, right?
No, that one's more about blood flow. So it's like blood flow biomechanics. So it's not listed yet, but I did request it. So I'll have to see if they say yes.
Any 500 level courses that you take?
So the only one that I probably would be 540.
Okay.
Yeah, and so I'd probably say it's a 70% chance that I teach that.
So by when do you think that we would get to know? Because some of us have taken, like me and my friends have taken that subject, so we would want to know if it's going to be you or someone else. So so then we can start planning.
Right. Yeah. So usually, I mean, the department chair just asked us today what we want to teach, and usually it takes them a couple of weeks to put that together. Usually I know before they put it on there, and so when I know, I'll let you know. But probably by Thanksgiving.
Cool.
Yeah, I'll let you know because I think they're not going to put it on the official schedule until like December.
Okay.
Yeah.
Thank you.
Yeah. Mm-hmm. All right, Zoom people, any final questions before I sign off? Okay. All right. So I'll see you guys next week.